orientation, then a reaction can take place to produce molecules of O2 and NO2.
So they found each other, had enough energy, and they were in the right orientation. Like, are you serious?
It's a lot of stuff.
Is there a way to make sure that always happens? They have sufficient energy and properly oriented?
If you jack up the temperature, that gives them sufficient energy. But then does this make sense? If they have sufficient energy, part of that energy is kinetic energy, so they're bouncing around. So are they?
Okay.
So you have to be a little careful with that. But that's for the energy barrier. And then this orientation would be the catalyst. And not all reactions lend themselves to a catalyst, I don't think.
Okay.
But good question. So reaction rates, things that affect reaction rates are how concentrated the reactants are. You guys saw, saw that in lab yesterday. As it was more dilute, what happened to the reaction rates? Slowed down. Right. Temperature, and we're going to actually look at that effect next Thursday. As you jack up the temperature, the reaction rate goes up. Surface area, to me, surface area kind of is back to, how do I say this? As you increase surface area, you increase reaction rates. And it's kind of like, are the reactants going to be able to find each other? I think that, to me, that's kind of, presence of a catalyst is just orientation. What's that? Mic coming? Okay. Okay, so if we didn't have kind of out of sequence yesterday when I kind of gave you, this is called a rate law expression. It's got several names, but the rate law expression for the reaction of interest. We already talked about these reaction orders, okay, a little bit. But does this make sense? If your M or N, if it's positive, okay, then can you see where if you increase the concentration, then your reaction rate will increase? Hi, Mike. Okay. The next one says for any reaction, it's kind of cool because it's fun when you can say for any reaction. If you increase the temperature, you're going to increase the reaction rate because of that middle factor. You give them enough energy to proceed from reactants to products. Greater surface area allows more contact. More contact means faster reaction. It's kind of intuitive. And the catalyst provides for the orientation to be proper. Yeah. So I think and gosh, it's been a long time, but the whole RNA, DNA, I mean, isn't it like one is like and then it breaks off and, yeah. So it's like a template sort of thing. So we're going to go on to the next slide, Mike.
Cool.
So I have some videos here. Effective concentration. Oops, go back.
In the test tubes is hydrochloric acid. On the left is a 0.3 molar solution, and on the right is a 6 molar solution. If we place a strip of magnesium metal in the 0.3 molar solution, the metal begins to react slowly. If we place a similar magnesium strip in the 6 molar solution,
oh, okay, I got it.
Much more vigorous.
Oh. Can you hear the vigorous?
Within moments, the reaction is complete. Meanwhile, most of the magnesium in the 0.3 molar solution is still in solid form.
Well, I don't have the patience to track that one down. Let's see, hopefully the next one is fine. This
On the
is
plate
surface
is
area.
a pile of lycopodium powder. If we aim a flame at it, not much happens. If, however, we take some of the lycopodium and then spray it into a flame, the combustion reaction is explosive. The more surface area of the lycopodium particles that is exposed to oxygen, the faster the reaction.
Well, that's fun.
Yeah, no, that was fun. Like around here, how does this work? Like silos will have issues with dust fires and stuff like that. To me, that's kind of what it kind of reminds me of. Let's see. One more. Catalyst.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces oxygen and water.
I'd say.
The manganese dioxide is not consumed or otherwise altered by the reaction. It serves only as a catalyst and makes the reaction occur more rapidly.
Giving proper orientation for it to decompose. That's cool. Very good. Okay, then the last slide is, this is what was due today.
Yes.
Okay. So on to, as promised, making a little more sense of what we did yesterday. Let's see, down here.
Guitars.
Okay. There we go. So up here, I went ahead, and this thing right here is a rate law expression, otherwise known as a rate expression, a rate equation, a rate law. Okay. So it's awesome. I mean, it's a mathematical statement, kind of like we do in like PV equals nRT. Like you plug it in, right? Plug in things and go. I'd probably call it a rate law expression right now anyway. And we're going to talk about it piecemeal throughout this unit, but we need to, in this rate law expression, take into consideration those three factors. Will they have sufficient collision? Will they have sufficient energy? Will they be oriented properly? Needs to be all kind of balled into this equation. All right. So A plus B goes to form products. I think I'll go ahead and change my thing up here. I'll put P for products. Now the little a and the little b, what are those? What?
The coefficient.
Coefficients, yeah. The little a and the little b are the coefficients, exactly. So this down here, this rate law expression, I kind of call the generic rate law expression from that particular thing. Now notice, and I'll try to kind of say why this is maybe, but notice that the reaction orders M and N are not the stoichiometric coefficients of the reactants. Okay. And what did the zero mean? What does the zero mean?
The initial.
Initial, exactly. So because the rate at the beginning is not the rate at the end, is it? It's going to slow down. All right. So this actually kind of says what everything is a little bit more, kind of like I did in pre-lab yesterday. If we go ahead and I'm going to change this to initial. If I change that to initial, I'm going to be looking at the initial change in the molar concentration of A, initial change in the molar concentration of B. I can do that. Okay. K actually, like this says, is dependent upon temperature for sure. It's also dependent upon the reaction. It's specific to the reaction. Bless you. And one of the things, and we're going to talk about it today, that Mike brought up is what are the units of K. Units, question mark? Okay, and the units of K depend actually upon what power you're raising these molarities to. And we'll talk about that, but the reaction rates, like you guys did in your homework, are gonna be are gonna be moles per liter per second, or per time anyway. Okay, so basically K kind of cleans up, I think, what's introduced by those two terms. All right, reaction orders. Whew. So reaction order is associated with a particular reactant. Okay, so we have a reaction order of A, and we have a reaction order of B. Now I've gone ahead and called it variable M and variable N. It could be anything though. And what those do is they say what this does is say how is the rate affected by the molar concentration of that particular reactant. How is the rate affected by the molar concentration of that particular reactant? And this is what I told you. So this M and N is not equal to A and B, okay? The reaction order for a reactant is not a stoichiometric coefficient. I think the reason students get confused is that here at the end of this unit, we're going to actually talk about what we call mechanisms behind the scenes, okay, like little chemical reactions behind the scenes that make the overall reaction of interest. In that case, the reaction orders are the stoichiometric coefficients. Notice how I kind of said it kind of lightly. Okay. You dealing with these elementary steps is not very light. It's a special type of problem. Okay. So how do we get them? Well, the reaction orders can only be gotten by running some experiments, just like you guys did yesterday. You guys ran like 4 experiments at different molar concentrations, and we talked about how graphically you could go ahead and plot the natural log of the rate over along the y-axis, the natural log of the molar concentration along the x-axis. Straight line should be positive slope, and the slope is the reaction order. Okay, so that's one way to take your experimentation and to get to your M and N. Now there's this important thing called the overall reaction order. So these are individual reaction orders, and it's not too hard. The overall reaction order is you just add these up. Okay, so for this particular scenario, I would get, overall RxN order, reaction order, is equal to M plus N. Okay, and like I said yesterday, these reaction orders don't have to be integers. We're going to kind of focus on at least starting out their integers. They don't have to be positive, but they most likely positive. Okay? All right. Well, the overall reaction order is important. I'm going to tell you why it's important. The overall reaction order will set the units of K. The overall reaction order will set the units of K, and this is what I mean. Well, I'm coming up to it. What else about reaction orders? Well, they can be positive or negative. Reaction orders can be 0. Okay. Check this out. What if I went ahead and put, for this M, what if I made that a 0? Okay, so it's A raised to the 0th power. What is molar concentration of A raised to the 0th power? It's 1. Yep. Anything raised to the 0th power is 1. So, dang, you start throwing in doubling the concentration of A, tripling the concentration of A, halving the concentration of A. Does it have any effect on your reaction rate? No. So it's kind of a fun thing. If a reaction order is 0, then that means that it does not affect reaction rate. Does that make sense? Yeah. So it can be 0. It's most likely positive. If it's negative, that kind of messes with my brain. If it's negative, that means as you increase it, the molar concentration, the rate decreases, doesn't it? That's kind of strange. I think I've run into those. They don't have to be integers. Most likely, if they're not whole number integers, they're like, I mentioned halvesies or thirdsies or something. Let's see. Now, the last bullet on there is that we are going to focus, we're kind of wimping out. Okay, we are going to focus on zero order, and we talked about zero order has changing the molar concentration has no effect on the rate. Okay, zero order, first order, and second order. Okay, all right. So I mentioned that the overall reaction order that you get by adding all of the reaction orders of all the reactants actually is going to set the units of K. And this actually came up with Mike. Mike said, what are the units of K? And I think of it in that whatever K kind of introduces something to cancel out whatever units are here so that we ultimately get moles per liter per time. So here's how this works. And you can kind of, try it out, convince yourself if you want. But if your overall reaction order, you add these up and it's 0, okay, then that means that there's no effect by anything here. So if your rate needs to be moles per liter per second, then your K must be moles per liter per second. Okay, if it's overall 0 reaction, which is kind of weird, okay, then your K is moles per liter per second. Make sense? Well, if you have an overall reaction order of 1, that means that here you introduce a moles per liter, okay? So then that means your K, needs to be per time or per second to get this. Right. Yay. And then the last one we're going to worry about is second order overall reaction order. If it's squared, okay, basically you have introduced a moles per liter squared. And then in order to get this, you have to go ahead and, how do I say this? You need to cancel one of those, right? Because you only need one at the top and you've got 2. Cancel one of those, and you need to also introduce time in the bottom. So basically, I don't know if you see this over there, you have 1 over molar per time. And 1 over moles per liter actually is the same thing as liters per mole. So that's kind of, this is the inverse of molarity here. All right. So looking at it a different way, so 0 we said if it's overall reaction order 0, then K needs to be units of moles per liter. Different ways of looking at that, moles per liter over time, is these 3 are all saying the same thing. And we said if it's first order overall reaction order, it needs to be inverse time. And I will say that these slides are pretty important in that this actually is a way, how do I say this? You got to do a little bit of detective work. If somebody gives you a K value and the units of K are just inverse time, you're like, I got this. If the units of K are inverse time, then you know that actually it's overall first order, okay? So you do a little bit of detective work. If the units of K that they give you are inverse molar per time, then you know you're looking at second order. Okay. So, all right. So here we go. We're going to look at, kind of think through this. It's kind of some data. Kind of like what you guys did in the lab. You did 4 trials at 4 different molar concentrations. We're going to look at 2 trials here. We're going to look at, and we're going to change the molar concentration of A. Okay, this is actually taking 2 reactants, like I have on the board, A and B. We're going to combine them together to form products. Okay, based upon that, we know that the generic rate law expression is this, for that's on the board there. So we're going to change it up. In the first case, we're going to say that we're going to put a real number in there. We're going to say that the initial molar concentration of A is 0.20 molar. And then we are going to double it. So for our second experiment, we're going to change it up. We're going to call it A2. And we're going to change it up. We're going to multiply the original initial concentration by 2. And so instead of 0.20 molar, we're going to be 0.40 molar. Okay, so you kind of got that right. We are going to, we're going to hold the molar concentration of B constant, kind of like what you guys did in your experiment yesterday. Now, this is kind of the magic, how this works. Let me grab a different color pen. K, obviously, rate law constant. We good with that? In our experiment we're going to do here, we are going to hold this constant too. Okay? So the observed rate is equal to some constant times the molar concentration of A, which I'm going to change from 0.2 to 0.4, times another constant. Okay? We do this a lot, or not a lot, I guess a lot. I'm actually going to combine these two, okay, and I'm going to make another constant. And guess what letter I'm going to use? K, yep. I'm going to rewrite this up here. I'm going to say initial rate is equal to, but I'm going to do a prime. K prime times the molar concentration of A raised to its reaction order. And then usually what I do is I say K prime, I say K prime really is this times this. K prime is really the original rate law constant K times the molar concentration of B raised to its reaction order, which I am holding constant. Okay? Seems fair. Seems legit. Okay? Good. All right. So that's not why my rate law expression says this at the top of the next page. The rate law expression, since I'm holding B constant, I'm going to bring it into my K, and I'm going to call it K prime. We'll call it a pseudo-constant. It is. The word pseudo, that's kind of a cool word. Is it PS pseudo constant? Yeah. Gotta love them. Yep. All right. Whew. With all that background, here we go. We're going to look at 4 different scenarios, okay, where we're changing the molar concentration of A. We're doubling it in each case. Here we go. This first scenario. All right, so let's look at it. Okay, you see the doubling, the 0.2 and the 0.4. Now, that number there is like the relative rates. So our relative rate was 1 with the 0.2. Our relative rate was 1 with the 0.4. Do you buy what the comment section says then?
Yeah.
Okay, good. So if your observed change is 0, then the M in this case, its reaction was 0. That's it. All right. Different reaction, because it can't do it, different reaction. You have to change gears. What if we go ahead and we double it, and our observed change, it increases by a factor of 1.4. First off, well, I guess I'm going about this wrong. We know it's 0.5, so our M is 0.5. 0.5 there, 0.5 there. If you, which is what, isn't that the square root of, right? Okay. No. Yeah. So if you go ahead and take 0.2 raised to its reaction order, you get 0.45. If you take 0.4 raised to its reaction order, you get 0.63. Now, if you take, and you guys are going to be doing some of this, this 1.4, it came from taking the 0.63 and dividing by 0.45. So if you want to put that in your notes somewhere, you can. So the observed increase was 1.4. And actually, I'm, excuse me, pretty sure this is how this works. You guys can track it down if you want to. You could go ahead and double anything. You could double any molar concentration, raise it to the 1/2 power, and your ratio is going to be 1.4. Isn't that kind of cool? Now, we don't deal a lot with half reaction orders, but that's how that works. We deal more with the 0, 1, and 2. So let's take a look at if it's 1. If its reaction order is 1, then we're going to take 0.2 raised to the first power, and we're going to take 0.4 raised to the first power, which is 0.2 and 0.4 respectively. Now, again, relative rates wise, if we take the faster rate, the 0.4, and divide by the slower rate, 0.4, and divide by the slow rate, 0.20, you get a factor of 2, right? So it's twice as fast. So my thing where it says kind of comment section, if you observe a twice as fast by doubling the molar concentration, you know it's first order. That's it. That's totally it. And we're going to kind of rely on that in the homework that's going to be due on Monday. The last one I said is second order with regard to this reactant, second order. So if it's second order, we're going to have to square molar concentration. So 0.20 squared is 0.040. 0.40 squared is 0.16. So if we take the 0.16 and we divide that by 0.16 relative rate, and we divide that by 0.040, you get a factor of 4, which is what we say when we say quadruple. So anytime you see a factor of 4, by doubling, this has to be doubling. That's the only way this can work. Yeah, I think so. You double the molar concentration and the rate quadruples, that means the reaction order of that reactant is 2. Did I say it wrong? Double the concentration and quadruples, the rate quadruples. That's what it is. Reaction order is 2, okay? So on this slide, the important things are kind of the observed. Stays the same, okay? It doubles, it's first order. It quadruples, it's second order. Those are the important things. Okay, so series of experiments is run. So, yeah. The only way, and sometimes this turns into a test question, the only way you can get these reaction orders for an overall reaction of interest, reaction orders have to come from experimental data. So you're going to run a series of experiments kind of like you did yesterday, and then you have a few options with what you do with them, your data. You guys are going to graph them. We can also do it by inspection. We can also do an algebraic approach to kind of tease out that information from your data. Just like we did here with this, this example, I said B has to remain constant. I think the word is confound. You don't want to confound your experiment by changing both. Initial rates are measured. And just like we did with A, since the only thing we were changing was molar concentration of A, any changes in the reaction rate had to do with the effect of changing that. That's why you hold everything else constant, unless you want to get a very big headache. It's called experimental design. All right. So, after you have your data, just changing one variable, the molar concentration of only one of maybe several reactants, you have a choice. Graphically, that's what you guys are doing in lab. Okay, you're basically taking your lab data, putting it on a plot, taking the log of the rate and the molar concentrations, getting a straight line, and getting the reaction order there. You can do it by inspection, and actually that's what we kind of did just a minute ago, just by inspection. The other one is algebraically, and I'll show you what that looks like. That one gives me a headache. So then I have one more thing to talk about. It looks like this. So we're going to do an example, and we're going to apply the by inspection. One of the things, let's see, how do I say this? This is the reaction of interest. Okay. Is this what I want to do? So from that reaction of interest, what I usually tell students, if you know that you're dealing with rate laws, write the rate law expression. So in the bottom here, I'm going to write what I call the generic rate law expression. So here we go. Okay, the rate for this, I can call it the initial rate. Probably should be better here. Initial rate, okay, is equal to the rate law constant K, and it's the molar concentration of each of the reactants. So we're going to have to put molar concentration of H2O2 raised to M, its reaction order, times the molar concentration of I minus raised to N. We don't know what that is. And guess what? Molar concentration of the hydrogen ion raised to the letter O, MnO, right? So we're supposed to use the data on the next page to come up with some things. And those things right here where it says the reaction order for each reactant, guess what? That is our M, N, O. The value of the rate law constant, well, that's right there. And then the appropriate rate law expression, I guess my note here would be to plug back in. I'll just put plug reaction orders back in, RXN orders back in. And when I say back in, I mean back into the thing I have at the bottom of the slide there. Right. So here we go. Yeah, I went ahead and printed out a copy, so it makes sense to me. So we have initial molar concentrations of everything, and then how fast did the reaction go? Kind of like what you guys did in lab yesterday. Okay, so the initial molar concentrations of our first trial are given here of the 3 reactants, and how fast did it go? 1.15 times 10 to the minus 6, that seems pretty, I don't know if that's fast. Moles per liter per second. I don't know. Okay, molar per second. Well, we ran it a second time and changed it up a little bit. Now, what's the difference between our first trial and our second trial? What do you think? Which one did we change?
Concentration of the H2O.
Yeah, we changed the concentration of H2O. Did we change anything else? Nope. Did our rate change? By a factor of, is it the
2.
same, double or triple, quadruple? Yep, double. Yep, very good. So since this is 2 times, based upon what we talked about a minute ago, what do you think the reaction order of the H2O2 is? 1. Very good. That's it. That's totally it. This is by inspection. Very good. Let's see, we ran it a 3rd time. Now sometimes you're like, okay, you ran it a 3rd time, so why? And you never know which to compare, but I'm looking at 1 and 3. What do you think is different there? Yep. Again, we doubled it. What happened to the rate? It doubled, yep. And so what is the reaction order of I minus? It is 1. Yes. Very good. Perfect. And then last but not least, let's compare 1 and 4. What did we change there? The H plus, yep. What happened to the reaction rate? No change. So what's the reaction order of H plus? 0. It is 0. That's it. This is by inspection. You got it. So then these kind of,
So,
yes.
and it'll only double it if you double the concentration, something like that.
Let's see. You have to hold everything the same except for 1. You
Yeah.
have to, yes.
But so, in both these, you double the concentration of both the iodine and the H2O2. So, but what if you triple the concentration, would that change the reaction order?
I think you'd have to, I would have to think through it. I don't think you'll get a doubling. You have to go back and you can mathematically figure out what it is, kind of doing the A thing. But it's not going to be, if they're first order, it's not going to double. It's going to do something else.
Okay, but like for all the homework problems and the test problems, it would usually be like double and stuff like this, right?
For this sort of by inspection, yes.
Okay.
Yes. And we're gonna, it's the algebraic approach, I said that kind of gives me a headache. In that case, it's not doubled, so you have to algebraically kind of finesse your data to get to your reaction orders. But if it's a simple doubling, can you use the rule if the reaction order, or excuse me, if the rate doubles, first order, if the rate quadruples, second order? Yeah. Yeah. I guess for any amount you're increasing a reactant, if there's no effect, it's always going to be 0. So, yeah. So that would be, yep, you're right. It's kind of specific. Yep. So to determine the reaction order for a particular reactant, you need to find 2 experiments where only one thing was changed. The concentration for one reactant was changed. And so for your the homework that's going to be due on Monday, you're going to see, you'll be able to see that it was always doubled. So we kind of already, I'll put these all up here. This slide actually summarizes what we just did a minute ago. With all 4 trials, this is what we did. When we wanted to get to the reaction order for the hydrogen peroxide, we combined experiment 1 and 2 because hydrogen peroxide was the thing that was changed, not the iodide or the hydrogen ion. You guys told me reaction order 1 because the rate doubled, and you were right. And then we combined 1 and 3, where the only thing that changed was the I minus. The rate doubled, so that meant that its reaction order is also 1. And then we compared 1 and 4, where the only thing that changed was the hydrogen ion. There was no change in the reaction rate, so that made it reaction order 0. So M is equal to 1, N is equal to 1, O is equal to 0. Okay, so we actually answered, I think, the first question now. So the next question is we need to get at K. And at this point, do you see where we can plug back in? To me, this is kind of like answering the last question. What is the rate law expression? And I can never know, just to be totally honest with you, full disclosure. So rate law expression, do we put the value for K there, or do we just go with the variable K? And I think that actually we just put the variable K in there. Now some of you guys might say, can we simplify this? And how would we simplify it? Okay. Yeah, exactly. Take out the hydrogen. Because this, anything raised to the 0th power is 1. So we can go ahead and take that out. So rewrite it like this. So if you ever see a rate law expression and it's missing one of the reactants, raised to its reaction order, Well, its reaction order must be 0. So it's just not included there. So that actually answers the third question. Now we need to go back and get a value for our K. And at first blush, you're like, how in the heck do we do that? And the answer is just substitute in for any of your trials. So for any trial, you know the molar concentration of everything and the rate. So you pick one, substitute in, and get your K. So that's what I've done here. To find the value of the rate constant K, once we have our M and N, all we got to do is rearrange it. But if you're like me, you've got to be careful rearranging, because that's where you like divide by the wrong number, divide by the wrong thing. And you don't have to pick the first one, but that's what I usually do. So taking the rate law expression and rearranging it to solve for K, we're going to take that last column, the initial rate, and we're going to divide by the molar concentration, excuse me, the hydrogen peroxide. Now, don't lose track of the important work we did before. We said that that's first order, and that's first order, right? Okay. So if you want to be redundant, feel free to put a superscript 1 up there, first order and first order. So if we put those 3 numbers in for the first trial, and if I was doing this, especially if I wanted to convey to the reader of my working this problem, really what I did, I probably would say using data from the first experiment. If you want to keep the professor guessing, just don't tell him which one you're using. But so that last number is 1.15 times 10 to the minus 6. Units are moles per liter per second. In the denominator, we have the hydrogen peroxide concentration, 0.010 moles per liter. Also then, for that trial, we had the I minus is 0.010 moles per liter. And this is a good example. This is our first K that we're coming up to. We said that if it was an overall second reaction order, we said it should have units of 1 over molarity and time. In other words, liters per mole time, didn't we? So let's see if that's what we get unit-wise. So let's see, 1 moles per liter, and that leaves units of, move these up, liters per mole second. Does that work for you? I think so. Round to 2 significant figures, you get 0.012. And units, like I said, would be liters per mole second. And again, I'm not a math teacher, but moles per liter cancel. We still have seconds in the denominator of the numerator, and we have moles per liter in the denominator. You bring them up, you flip them over, and you take the seconds and put it in the denominator.
How did the seconds get in the denominator?
Because it was in the denominator of the numerator.
Okay.
Sounds like doublespeak, I know. So, okay. So this is the one I want you to look at and take a look. This is out of order, and we'll kind of look at it together. But what you're going to see here in a minute was, what was that? We're going to see the 4 trials, and we're going to, by inspection, come up with the reaction orders. So 411 is due Monday. I can't let you have nothing to do over the weekend.
Just 411?
Just 411,
Okay.
yes.
Nice.
I know, and it's by inspection. And 1411, excuse me, yeah, 411. Yeah, it looks like this. Okay, so 4 trials. Now notice they're kind of uglier numbers than usual. You're like, what the heck? But we definitely have doubling and quadrupling in there somewhere. So my hint is to first write your generic rate law expression. Okay, what else did I say? Okay, what is the reaction order? To find the reaction orders, choose a pair of experiments where only one concentration was doubled. Okay, and compare the rates. Now, the rates they're not as obvious as the ones we just had. So remember, you're gonna have to actually divide the faster one by the slower one and see what you got, what factor you got. But trust me, it'll be very similar to what we did in lecture. What else do I have? Blah, 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 blah. Looks like I did 1 and 3. Yeah, you can kind of see, it's very similar. Okay, the overall reaction order, what mathematical operation do you do? Is it multiplication, division, addition, or subtraction?
Addition.
Addition, yes. Overall reaction order, just add those integers. This time they'll be integers, they don't have to be integers, yep. A quick addition for B. And for C, it's kind of like what we just did. Once you have your reaction orders, go ahead and pick a trial. Do me a favor, tell me which trial you pick. Substitute back in and find K. Okay? Yay. We'll see you on Monday.